I'm Roland Minton. These are some of my favorite math stories. In this episode, Mathematics is Sacred. We'll explore the temple geometry sangaku of Japan and the activities of the samurai in the 17th, 18th, and 19th centuries. Most of my information comes from the beautifully produced book, Sacred Mathematics, Japanese Temple Geometry. If that introduction brought to mind bloodshed and action-filled battles because of samurai, I should apologize. Ken Watanabe does not feature in this episode. As well, if the sacred part of the book title brings to mind hidden codes and mystical numerology, more apologies. There is no Dan Brown in this episode. What you will get is a brief introduction to the fascinating world of the uniquely Japanese sangaku and temple geometry. The word sangaku means mathematical tablet, and there are over 900 of them still hanging in Shinto shrines and Buddhist temples throughout Japan. It is believed that thousands more have been lost to time. A brief history lesson is necessary here. The Tokugawa shogunate ruled Japan from 1603 to 1868 and isolated Japanese from outside influences for most of this time. Very little movement across the border of people or ideas occurred. Japanese mathematics therefore developed independently of the massive achievements in other parts of the world. The Japanese were highly creative and found many of the results celebrated in Europe, India, and China. Unfortunately, they never fully developed calculus or its applications. The flourishing of mathematics and other aspects of culture were promoted by the over 200 years of peace in Japan. They had printed texts, having had the printing press before Europe did. Although they did not establish universities, they had a far-flung educational system that taught the 3 R's, reading, writing, and arithmetic, to a majority of citizens. The earliest known math text was published in 1627, and it included a method for calculating pi. The Japanese developed several techniques for solving higher-order polynomial equations. For example, x to the fifth minus x squared plus 4 equals 0, which has degree, the largest exponent, of 5. They solved one of degree 1024, solved by reducing it to an equivalent equation of degree 10 and solving that numerically. They were good. I mentioned the samurai in the teaser. With no wars to fight or rebellions to stop, this highly educated and privileged class became a primary source of teachers for the many small private schools throughout the country. I do enjoy the mental image of a samurai teaching math class, being old enough to think of John Belushi's sketches on Saturday Night Live. Many young and old learners were inspired by the texts and the samurai to create mathematics on their own. Isn't that a wonderful idea? To disseminate their work, they created sangaku, tablets, often highly decorated and artistic, illustrating the result. Most showed solutions only. This was to save precious room, but also served as a challenge to others to solve the problems themselves. The earliest known sangaku dates to 1683, but they may have been widespread earlier. The shrines and temples were obvious places to post them because of the long-standing custom of presenting gifts and artwork to the gods. This aspect of the sangaku helps explain why so many are true works of art and suggests that the offerings may have been partly in thanks for help finding the solution while seeking inspiration for further results. The book Sacred Mathematics includes many examples of varying difficulty. Here's one of the easy ones to give you a flavor. The image is not great, but the corresponding sangaku is the second from the left here. The problem, stated in our current language, is to consider a circle of radius r inscribed in an isosceles triangle with sides a and b as shown. If a equals 12 and b equals 10, find the value for r. You might want to try this before I give you the answer, which is 3. Here's one solution. Draw in an altitude of the triangle, call it h, and a radius of the circle touching the left-hand side, b. First, focus on the small triangle upper left. The length of the vertical dash segment is h minus r. The full length of the dash is h, and we have removed a segment of length r. The angled dash segment is a radius of the circle and has length r. We have a right triangle, and the sine of the angle sketched in is opposite divided by hypotenuse, or r divided by h minus r. Now look at the larger triangle shown as the left half of the full triangle. The length at the bottom is a over 2, and the hypotenuse is b. The sine of the angle sketched in is a over 2 over b. Both fractions represent the same value, so they're equal. R divided by h minus r equals a over 2 divided by b, which can be manipulated to get r equals ah divided by a plus 2b. Now going back to the right triangle shown, the Pythagorean theorem gives h squared plus a over 2 squared equals b squared. Substituting in a equals 12 and b equals 10 lets you solve for h equals 8. With this value, the radius r equals ah over a plus 2b gives r equals 3. Well, maybe not so simple. Sangaku gives us a look at how mathematics developed in a country working independently of the rest of the world. Fascinating and beautiful.